48 light-years from Earth, something impossible exists. A planet nearly 3 times the size of our world, wrapped in clouds so thick they've hidden its secrets for over a decade. Scientists called it a water world. They were wrong. What they discovered instead challenges everything we thought we knew about how planets form. JJ1214b refuses to fit into any category we've created. It's not a rocky planet like Earth. It's not a gas giant like Jupiter. The thing sits in a gap that shouldn't exist, occupying a size range completely absent from our solar system. And here's what makes this deeply strange: planets like this are the most common type in our galaxy. We're surrounded by worlds that have no equivalent in our cosmic neighborhood. We've been studying the exception, not the rule. In December 2009, when astronomers first spotted this planet transiting its distant red star, they thought they'd found something straightforward. A super-Earth, maybe. Perhaps an ocean planet with endless seas beneath thick skies. The initial measurements seemed to confirm it. Low density. The right size. A composition that could match liquid water under intense pressure. Scientists started building models of exotic water phases, imagining hot ice and superfluid oceans that defied normal physics. Then the clouds appeared. Every attempt to peer into the atmosphere hit the same wall. Hubble looked. Spitzer looked. Ground-based telescopes strained to catch a glimpse of what lay beneath. Nothing. Just an impenetrable haze reflecting starlight back into space, keeping its secrets locked away. For over 10 years, JJ1214b earned a reputation as the white whale of exoplanet research. The one that got away. The planet that refused to be understood. Until James Webb changed everything. But we're getting ahead of ourselves. To understand why this planet matters, why scientists spent more than a decade obsessing over a world they couldn't see clearly, you need to know what makes it so fundamentally different from anything orbiting our sun. Start with the basics. JJ1214b has a mass 8.41 times that of Earth. Its radius stretches 2.733 times wider than our planet. Plug those numbers into the density equation and something immediately feels off. 2 grams per cubic centimeter. Earth clocks in at 5.5. That's not a small difference. That's the difference between solid rock and something far lighter, far stranger. The planet screams around its star in just 1.6 days. 1 orbit. 38 hours. By the time you finish a weekend, JJ1214b has circled its sun more than once. It huddles close to its parent star, only 0.01505 astronomical units away. For context, Mercury orbits our sun at 39 cents. This planet sits 70 times closer to its star than Earth does to ours. That proximity creates something we rarely see. Tidal locking. The same face perpetually stares at the star while the far side dwells in eternal night. One hemisphere bakes under constant radiation. The other freezes in permanent darkness. The temperature difference between the two sides spans 115 degrees Celsius. Imagine a world where the concept of sunrise doesn't exist, where half the planet has never seen its star and never will. The parent star itself adds another layer to this puzzle. JJ1214 measures about 1/5 the radius of our sun, with a surface temperature of 3110 Kelvin. Its luminosity barely reaches 0.35% of what our sun produces. This is a red dwarf, a dim coal in the cosmic furnace, yet its proximity to the planet creates surface temperatures between 120 and 282 degrees Celsius. Hot enough to boil water at Earth's atmospheric pressure. Too hot for life as we know it. Yet this small, cool star became the perfect laboratory. Because GJ1214 is dim and small, when the planet passes in front of it, the transit signal becomes pronounced. The planet blocks a larger fraction of the star's light than a similar-sized world would around a sun-like star. This makes observations easier, signals clearer, data more precise. Sometimes the universe hands you exactly what you need. Scientists knew from the beginning they were looking at something unprecedented. After Corot 7b, GJ1214b became only the second planet between Earth and Neptune in mass to have both dimensions precisely measured. More importantly, it represented the first of a new class. Small size. Low density. A composition that didn't match rocky planets or gas giants. The discovery came through a collaborative effort that showcased modern astronomy at its best. The M-Earth project, a network of small robotic telescopes designed to monitor nearby red dwarfs, caught the initial transit. Then ESO's HARP spectrograph at La Silla confirmed the discovery, measuring the planet's mass through the tiny wobble it induced in its star's motion. Harvard-Smithsonian astronomers announced the find in mid-December 2009, and immediately the theory started flowing. Water world. The term spread quickly through research papers and press releases. The density matched. The size worked. Models suggested a composition of roughly 25% rock and 75% water, wrapped in a thin envelope of hydrogen and helium. Scientists started imagining what such a world might look like beneath those clouds. The pressure at depth would transform water into forms that don't exist on Earth's surface. Steam in the upper layers, transitioning to liquid, then to exotic high-pressure ices that remain solid at temperatures hot enough to boil normal water. Ice 7, with its cubic crystal structure instead of the familiar hexagonal pattern. Superfluid water with zero viscosity, flowing without friction in ways that defy intuition. Some models even suggested plasma phases of water, where the intense heat strips electrons from molecules. Europa, Jupiter's ice-covered moon, became the common comparison. Think of GJ1214b as a bigger, hotter Europa. A world where water dominates, where oceans might stretch hundreds of kilometers deep, where the boundary between liquid and solid blurs into strange intermediate states. Except Europa doesn't have an atmosphere thick enough to hide everything beneath it. Those clouds became the central mystery. Every time scientists pointed a telescope at GJ1214b during a transit, trying to analyze the starlight filtering through the atmosphere's edge, they got nothing. No spectral features. No chemical fingerprints. No absorption lines indicating water vapor, methane, carbon dioxide, or any other expected molecule. Just a flat, featureless spectrum that told them only one thing: something was blocking their view. Cloud-free atmospheric models failed immediately. Compositions dominated by water, methane, carbon monoxide, nitrogen, or carbon dioxide couldn't explain the observations. The confidence level exceeded 5 sigma. In particle physics, 5 sigma means you've discovered something real. In this context, it meant you could rule out clear skies with near certainty. So the planet either had an atmosphere of relatively heavy molecules creating a thick haze, or it had high-altitude clouds made of materials that reflected and scattered light with unusual efficiency. Or both. The data couldn't distinguish between these scenarios. Every model that fit the observations required something blocking the view from above. One researcher captured the frustration perfectly, calling GJ1214b the white whale of exoplanet atmosphere characterization. The whole community chased it for years. The planet sat close enough to study in detail, transited regularly for repeated observations, and represented an entirely new category of world. Yet it refused to yield its secrets. Then in 2022, something shifted. The planet and its host star were included among 20 systems selected for the third Name ExoWorlds project. A team from Kenya proposed names drawn from the Ma language of the Maasai people. In June 2023, the International Astronomical Union made it official. JJ1214b became Enoposha, the Ma word for a large body of water. Its star became Orcaria, meaning red ochre, referencing both the star's color and the iron-rich Earth. The naming reflected what scientists believed at the time. A water world orbiting a red star. The cultural connection honored the Maasai people's relationship with natural elements while giving this distant planet an identity beyond its catalog designation. Enoposha. A name that evoked oceans in depth, mystery, and abundance. But names, like first impressions, don't always capture the full truth. By late 2024, new data was emerging from an observatory that hadn't existed when JJ1214b was discovered. James Webb Space Telescope, with its massive mirror and unprecedented sensitivity in infrared wavelengths, had finally turned its attention to the white whale. The team took a different approach than previous attempts. Instead of just catching the planet during transit, they tracked it through an entire orbit. 40 hours of continuous observation. Day side. Night side. Everything in between. What they found would rewrite everything. The mid-infrared instrument on James Webb, known as MIRI, operates in wavelengths between 5 and 28 micrometers. That range captures thermal emission directly from planetary atmospheres. Not reflected starlight bouncing off clouds, but actual heat radiating from the planet itself. Previous telescopes like Hubble and Spitzer had looked at Enoposha, but they observed in different wavelengths, trying to catch subtle variations in starlight during transits. Those observations told scientists that something was blocking their view. JWST could see the planet glowing with its own heat. The observation window opened in late 2022. The team programmed JWST to lock onto the JJ1214 system and stay there. Not just for a single transit, but for 40 continuous hours. The planet completes one orbit every 1.6 days. 40 hours meant capturing more than one full revolution. Dayside facing the star. Nightside turned away. Everything in between. During those hours, MIRI measured the infrared brightness of Enoposha thousands of times. Each measurement captured the thermal glow from different parts of the planet as it rotated and orbited. The data formed what's called a spectroscopic thermal phase curve. Think of photographing the moon through a full lunar cycle, except instead of visible light, you're recording heat signatures. And instead of a month, it happens in less than 2 days. When the analysis began, patterns emerged immediately. The dayside showed an average brightness temperature of 553 Kelvin, plus or minus 9 degrees. That translates to about 280 degrees Celsius. Hot enough to melt lead, but cooler than scientists expected for a planet orbiting that close to its star. The night side measured 437 Kelvin, plus or minus 19 degrees. Roughly 164 Celsius. Still scorching by Earth standards, but significantly cooler than the illuminated hemisphere. That temperature difference, 115 degrees between day and night, revealed something critical about how the atmosphere works. If heat moved efficiently from day to night, the difference would be smaller. The large gap suggested the atmosphere doesn't redistribute thermal energy very well. Winds exist, but they're not strong enough to even out the temperature extremes created by tidal locking. But temperature distribution was just the beginning. The real breakthrough came from the spectroscopic part of the observation. MIRI didn't just measure overall brightness. It broke the infrared light into different wavelengths, creating a spectrum. Different molecules absorb and emit light at specific wavelengths. Water vapor has a signature. Carbon dioxide has another. Methane, ammonia, each leaves distinct fingerprints in the spectrum. Both the dayside and nightside spectra showed absorption features. More than 3 sigma confidence level. In statistical terms, that means the signal stood out clearly above background noise. The most likely explanation for these features: water vapor. H2O molecules in the atmosphere absorbing specific infrared wavelengths. That discovery alone would have been significant. Direct detection of water vapor in a sub-Neptune atmosphere. But the data contained more. The overall thermal emission pattern, combined with how much starlight the planet reflected, pointed towards something unexpected. The team calculated Enoposha's bond albedo at 0.51, plus or minus 0.06. Bond albedo measures the fraction of incoming starlight reflected back into space. Earth's bond albedo sits around 0.3. Venus, with its highly reflective cloud deck, reaches about 0.75. Enoposha fell in between, but closer to Venus than Earth. That high reflectivity explained why the planet wasn't hotter. It was bouncing half the star's energy back into space before that radiation could warm the atmosphere. What creates such strong reflection? The haze layer. That same obstacle that had frustrated astronomers for years was now revealing its properties. The haze reflects radiation without absorbing it and heating up. Maria Steinruck from the Max Planck Institute for Astronomy noted that the composition must differ from any known celestial body. The usual candidates, water ice clouds, hydrocarbon hazes, sulfur compounds, none matched the observed properties perfectly. The team ran the observations through three-dimensional atmospheric models. These simulations recreate the physics of planetary atmospheres, tracking how gases flow, how heat moves, how chemicals interact under different conditions. The models tested various scenarios. Different compositions. Different cloud properties. Different haze distributions. Only one type of configuration consistently matched the data. High metallicity atmosphere. Not metallic in the sense of iron or copper, but astronomically metallic. In astronomy, anything heavier than hydrogen and helium counts as a metal. The models showed that Enoposha's atmosphere contains vastly more of these heavy elements than expected. Not just twice or 5 times solar abundance. More like 100 times. Some calculations suggested up to 1,000 times. That extreme enrichment changes everything about how the atmosphere behaves. Hydrogen and helium-dominated atmospheres, like Jupiter's, are relatively transparent in many wavelengths. They're puffy, extended, easy to study spectroscopically. Heavy molecule atmospheres are denser, more compact, and they produce different chemical species when stellar radiation breaks them apart and recombines them. The water vapor detection fit this picture. With that much oxygen and hydrogen available in heavy molecular form, H2O becomes abundant. But it's not the only possibility. The spectral features could also indicate methane, CH4, or a mixture of both. The current data can't distinguish completely. What's certain is that the atmosphere contains significant amounts of molecules much heavier than the hydrogen-helium mix that dominates gas giant planets. This discovery demolished the water world hypothesis. Not because water isn't present, water vapor clearly exists in the atmosphere, but because the planet's structure can't support the original model. A world that's 75% water by mass, covered with a thin hydrogen-helium envelope, doesn't produce the observed properties. The high metallicity requires a different internal architecture. The maximum hydrogen-helium content, based on the planet's mass and radius, caps out at 5.8% of total mass. That's a relatively small envelope compared to Neptune, which is roughly 20% hydrogen and helium. The bulk of Enopotia must consist of heavier materials. Rock in the core, certainly. But the envelope itself is dominated by volatiles like water, methane, and carbon dioxide in some combination, not the light gases that make up Jupiter and Saturn. Then came January 2025. Another team published spectroscopic analysis revealing atmospheric contents that looked metallic in composition. Carbon dioxide acting as an aerosol, suspended in the upper atmosphere. The layout resembled what they called a super-Venus. Venus has a thick CO2 atmosphere with sulfuric acid clouds. Scale that up, make it hotter, add more mass, and you get something like Enopotia. This comparison marks how far our understanding has shifted. From ocean world to super-Venus. From Europa's bigger cousin to Venus on steroids. The transformation didn't happen because scientists were wrong initially. It happened because they finally got the data needed to see past the clouds. The JWST observations represent the first direct detection of light emitted by a sub-Neptune exoplanet. Not starlight filtering through the atmosphere during transit, but thermal radiation from the planet itself. That distinction matters. Transit spectroscopy reveals what's in the upper atmosphere where starlight passes through. Emission spectroscopy shows the deeper atmosphere where the planet generates its own heat signature. Combining both techniques creates a three-dimensional picture. Upper atmosphere composition from transits. Lower atmosphere and temperature structure from emission. Day and night variations from phase curves. Together, these observations constrain the models far more tightly than any single method could. The haze layer itself became a focus of intense study. It sits high in the atmosphere, reflecting half the incoming starlight without heating up significantly. That behavior requires specific optical properties. The particles must be the right size to scatter visible and near-infrared light efficiently. They must be chemically stable under intense stellar radiation. And they must form continuously, because atmospheric processes would gradually remove them if production stopped. Photochemistry likely creates these hazes. Similar to how ozone forms in Earth's atmosphere when UV radiation splits oxygen molecules, stellar radiation breaks apart molecules in Enopotia's upper atmosphere. The fragments recombine into larger, more complex molecules. These molecules condense into tiny particles. The particles grow, clump together, and eventually become visible as haze. Organic compounds top the candidate list. Titan, Saturn's largest moon, has a thick organic haze created by photochemistry. Methane breaks apart under UV light, and the carbon atoms link together into long chains. Those chains form particles that give Titan's atmosphere its characteristic orange color. Enopotia might produce similar compounds, though at higher temperatures and under different radiation conditions. Sulfur-based hazes represent another possibility. Volcanic planets or those with sulfur-rich chemistry could generate particles containing sulfur compounds. These materials reflect light differently than organic hazes, potentially matching Enopotia's properties better. The truth probably involves multiple aerosol types at different altitudes. Condensate clouds lower down, where temperatures allow certain materials to transition from gas to liquid or solid. Photochemical hazes higher up, where UV radiation drives continuous particle production. The combination creates the thick, highly reflective barrier that's hidden this planet's nature for so long. What lies beneath that barrier remains partially unknown. The JWST data reveals the atmosphere's composition and structure to unprecedented depth, but the surface, if one exists, stays hidden. With temperatures exceeding 500 Kelvin globally, any surface would be hellishly hot. If water exists in liquid form, it would be under tremendous pressure, creating conditions utterly alien to human experience. But there's a deeper mystery emerging from all this data. One that extends far beyond a single planet. Enoposha represents a puzzle piece in a much larger picture. Subneptunes make up the most common planetary type in the Milky Way. Everywhere astronomers point their telescopes, they find these intermediate-sized worlds. Between rocky planets and gas giants. Between familiar and utterly strange. Yet our solar system contains exactly 0 examples. Not one planet fits this category. Earth, Venus, Mars, Mercury. All rocky. Jupiter, Saturn, Uranus, Neptune. Gas and ice giants. Nothing in between. That gap matters more than it might seem. Without local examples, scientists lack direct comparison points. They can't send probes. Can't measure directly. Can't test theories through close observation. Every conclusion about subneptunes comes from distant study of alien worlds around other stars. This makes Enoposha extraordinarily valuable. It sits close enough for detailed observation. 48 light-years sounds far, but in cosmic terms, it's practically next door. The parent star, or Carria, shines dimly enough that the planet's thermal emission stands out clearly. And the system's geometry works perfectly. The planet transits its star from our viewpoint, crossing the stellar disk every 1.6 days. That transit frequency creates opportunities. Most exoplanets take weeks, months, or years to orbit. Observing multiple transits requires patience and careful scheduling. Enoposha completes 60 orbits in under 3 months. Hundreds per year. This allows rapid data accumulation and statistical refinement that slower systems can't match. The metallicity findings shake fundamental assumptions. An atmosphere 100 to 1,000 times more metal-rich than the Sun defies easy explanation. Where did all those heavy elements come from? How did they concentrate so dramatically? Three formation scenarios compete for dominance. First, formation beyond the snow line. In the early protoplanetary disk, temperatures dropped with distance from the star. Beyond a certain radius, water and other volatiles froze solid. Icy planetesimals accumulated, building larger bodies. These ice-rich worlds contained more heavy elements than the hydrogen-helium-dominated inner disk. If Enoposha formed there, it would naturally possess higher metallicity. But something else happened later. The planet migrated inward, spiraling toward its current location. Gravitational interactions with the disk or other planets pushed it closer to Carria. As it approached the star, temperatures soared. Ice melted. Water evaporated. The atmosphere transformed from cold and ice-rich to hot and steam-dominated. Second, late-stage bombardment. After initial formation, the planet experienced intense bombardment by ice-rich comets and asteroids. Each impact delivered volatiles and heavy elements. Over millions of years, this continuous rain of material enriched the atmosphere far beyond its original composition. The process resembles Earth's late heavy bombardment, but on a scale that dwarfs anything our planet experienced. Third, preferential loss of hydrogen. The planet formed with substantial hydrogen and helium, similar to a mini Jupiter. But proximity to the star created problems. Stellar radiation heated the upper atmosphere. Hydrogen, the lightest element, escaped most easily. Over geological time, the planet bled hydrogen into space while retaining heavier molecules. This selective loss enriched what remained, creating an atmosphere dominated by water, carbon dioxide, and other heavy species. Each scenario predicts different observable signatures. Migration should leave chemical fingerprints in atmospheric composition. Bombardment would create specific isotope ratios. Hydrogen loss produces particular atmospheric profiles. Distinguishing between these possibilities requires more precise measurements than currently available. But the JWST data already constrains the possibilities. The carbon dioxide discovery adds another layer. Spectroscopic analysis detected weak but measurable CO2 absorption features. Not definitive yet. Statistical uncertainty remains. But if confirmed, it transforms the picture completely. Carbon dioxide dominates Venus's atmosphere. It creates the runaway greenhouse effect that turned our sister planet into hell. A thick CO2 atmosphere on Enopotia would strengthen the super-Venus comparison dramatically. Carbon dioxide forms through multiple pathways. Volcanic outgassing releases it from rocky interiors. Photochemistry can produce it from methane and water vapor. Impact events might deliver it directly. The presence of CO2 also affects everything else. It changes how the atmosphere absorbs and emits radiation. It influences cloud formation chemistry. It alters the planet's thermal structure from top to bottom. The reflectivity question demands answers. Bond albedo of 0.51 means half the incoming starlight bounces back into space. That's phenomenally high. Higher than any planet in our solar system except Venus, which reaches similar values due to its sulfuric acid clouds. What material achieves this on Enopotia? Sulfuric acid seems unlikely. The temperatures run too hot for sulfuric acid clouds to form at the right altitudes. The chemistry doesn't favor it. Titan's organic hazes reflect less efficiently. Water ice clouds could work, but they require specific temperature and pressure conditions. Salt crystals represent an intriguing possibility. Vaporized rock condensing at high altitude might produce reflective aerosols. But laboratory data on these exotic materials remains sparse. The haze layer's persistence poses its own mystery. Atmospheric dynamics should clear out particles relatively quickly. Gravity pulls them downward. Turbulence disperses them. Yet the haze maintains consistent optical depth over years of observations. This implies continuous production. Something constantly generates new particles to replace those lost. Photochemistry offers the most plausible mechanism. Stellar UV radiation provides steady energy input. It drives chemical reactions that wouldn't occur otherwise. Break molecules apart. Recombine fragments into new compounds. Condense those compounds into particles. Repeat endlessly. The day-night temperature difference reveals atmospheric behavior. 115 degrees Kelvin separates the hemispheres. That's substantial but not extreme. Some hot Jupiters show temperature contrasts exceeding 1,000 degrees. Others, particularly those with strong winds, show almost no difference at all. Enopotia falls somewhere in the middle. The atmosphere redistributes some heat but not efficiently. This inefficiency suggests limited wind speeds. On gas giants with rapid rotation and strong jet streams, heat moves quickly from day to night side. Temperature equalizes. Enopotia's slow rotation, locked to its orbital period, prevents strong Coriolis forces from developing. Without those forces, wind patterns remain relatively weak. Heat transport occurs mainly through slower processes like convection and radiation. Three-dimensional atmospheric modeling attempts to capture this complexity. Researchers input the planet's basic parameters: size, mass, orbital distance, stellar radiation. They specify atmospheric composition based on observations. They include cloud and haze layers with various optical properties. Then they let physics take over. The model calculates how gases flow, how radiation transfers energy, how chemicals react and transform. After thousands of simulated hours, a picture emerges. These models don't perfectly match reality yet. Too many unknowns remain. Cloud particle sizes, haze composition, atmospheric mixing ratios, chemical reaction rates at exotic temperatures and pressures. Each uncertainty introduces potential errors. But the models still provide invaluable insights. They show which scenarios work and which don't. They predict what future observations should reveal. They guide the next generation of telescope proposals. The tidal locking itself creates a fascinating environment. One hemisphere eternally faces Urcaria. The star hangs motionless in the sky. Perpetual day. Unending heat. The other hemisphere faces outward. Perpetual night. Relative cold. Between them, a terminator zone where day meets night. Temperatures gradient continuously. Winds blow from hot to cold. Chemistry shifts with altitude and location. If Enopotia possessed a solid surface beneath its atmosphere, which remains uncertain, that surface would experience dramatically different conditions depending on location. The subsolar point, directly beneath the star, would bake under continuous radiation. The antistellar point would radiate heat into space without replenishment. The terminator would exist in twilight, potentially offering the most moderate conditions anywhere on the planet. But does a surface exist? The density measurements suggest otherwise. 2 grams per cubic centimeter. Earth's density reaches 5.5. Rock and metal sink. Enopotia's low density implies a thick gaseous envelope surrounding a relatively small core. The atmosphere might extend down for thousands of kilometers before transitioning to supercritical fluids. Those fluids might grade continuously into liquid, then solid phases at the center. No distinct surface. Just layers of increasing density and pressure. This internal structure resembles Neptune more than Earth. But the composition differs radically. Neptune consists mainly of hydrogen, helium, water, methane, and ammonia. Enopotia's high metallicity demands a different mix. Water likely dominates, possibly in exotic high-pressure phases. Carbon dioxide might contribute substantially. Heavier molecules fill roles that hydrogen and helium play in larger planets. The formation history determines current state. If Enopotia formed beyond the snow line and migrated inward, it started as a cold world. Ice dominated the surface. Temperatures allowed complex chemistry. Water existed as solid ice, not steam. The migration itself would have been catastrophic. As the planet spiraled inward, stellar radiation intensified. Ice began melting, then vaporizing. The atmosphere swelled dramatically. What started as a modest envelope became a thick blanket of steam. Chemical equilibria shifted. New compounds formed. The planet transformed completely over millions of years. During that transformation, hydrogen and helium that originally cloaked the forming planet would have been partially or entirely lost. Intense stellar wind strips lighter elements away. Radiation heats the upper atmosphere until molecules escape gravitational pull. A young red dwarf like Orcaria produces energetic outbursts. X-ray flares blast the surrounding space. Ultraviolet radiation bombards nearby planets. For a world orbiting so close, atmospheric loss becomes inevitable. The hydrogen envelope evaporates first. Lightest molecules escape most easily. What remains concentrates toward heavier compounds. Water vapor. Carbon dioxide. Methane. These molecules possess greater mass. Gravity holds them more securely. Over millions of years, the atmospheric composition shifts radically. What began as a hydrogen-rich envelope transforms into something far more exotic. This evolutionary pathway explains Enoposha's current high metallicity. The atmosphere didn't start this way. Migration and stellar bombardment sculpted it. Each phase of the journey left chemical signatures. Current observations capture just one snapshot of an ongoing transformation. The comparison to Venus becomes increasingly compelling. Our solar system's second planet demonstrates what thick carbon dioxide atmospheres accomplish. Runaway greenhouse effects. Surface temperatures hot enough to melt lead. Crushing atmospheric pressure. Venus transformed from potentially habitable to hellish through atmospheric evolution. Enoposha might represent an extreme version of this process. Take Venus. Increase the mass. Move it closer to the star. Add exotic chemistry. The result resembles what James Webb detected. Carbon dioxide aerosols suspended above a metallic atmosphere. Reflective hazes bouncing radiation back into space. Temperature distributions that defy simple explanations. Recent spectroscopic analysis strengthens this interpretation. January 2025 observations revealed carbon dioxide acting as suspended aerosols. The configuration mirrors Venus but amplified. Super-Venus emerges as more than metaphor. It describes a genuine planetary category. Worlds that took the Venusian template and pushed it to extremes. This reclassification carries profound implications. For over a decade, scientists pursued the water world hypothesis. Models assumed liquid oceans. Calculations explored exotic ice phases, deep ocean currents, subsurface chemistry. The entire framework rested on fundamental assumptions about composition. Those assumptions now appear incorrect. Enoposha probably lacks vast liquid reservoirs. No global ocean several hundred kilometers deep. No ice layers transitioning through multiple phases. Instead, a thick gaseous envelope surrounds a relatively small rocky core. The water exists as vapor mixed into an atmosphere dominated by heavier molecules. does water still play a role? Absolutely. Spectroscopic signatures indicate water vapor presence. Absorption features in both dayside and nightside spectra point toward H2O molecules. But water as atmospheric constituent differs fundamentally from water as planetary bulk composition. One scenario imagines vapor mixed among other gases. The other envisions water defining the planet's entire structure. The metallicity measurements settle this distinction. 100 times solar metallicity minimum, possibly 1,000 times. Such extreme values demand heavy element dominance. Hydrogen and helium contribute at most a few percent of atmospheric mass. Everything else consists of compounds like water, carbon dioxide, methane, and more exotic molecules. This composition creates unique chemistry. On Earth, atmospheric chemistry involves nitrogen, oxygen, and trace gases. Familiar reactions. Predictable outcomes. On Enopotia, high temperatures and unusual molecular ratios generate unfamiliar pathways. Carbon dioxide might react with water vapor under intense radiation. Methane could break apart and recombine into complex organic molecules. Sulfur compounds might form hazes unlike anything terrestrial. Laboratory experiments attempt to recreate these conditions. Scientists fill chambers with appropriate gas mixtures. They irradiate samples with ultraviolet light matching Orcaria's spectrum. They monitor what molecules form. The results remain preliminary. Too many variables. Too many unknown reaction rates. But the experiments provide crucial constraints for atmospheric models. Photochemistry drives haze production. Ultraviolet photons strike molecules in the upper atmosphere. Chemical bonds break. Free radicals form. These reactive fragments collide and combine. Larger molecules gradually assemble. Eventually, particles grow large enough to scatter light efficiently. A haze layer develops. This process resembles what happens on Titan, Saturn's largest moon. Titan's atmosphere contains nitrogen and methane. Solar ultraviolet radiation breaks methane apart. The fragments create complex organic molecules called tholins. These tholins form an orange haze that completely obscures Titan's surface. Cassini spacecraft observations revealed this chemistry in exquisite detail. Enopotia's hazes might follow similar principles but with different starting materials. Carbon dioxide instead of methane. Water vapor instead of nitrogen. Higher temperatures accelerating reaction rates. Different pressure profiles changing which molecules remain stable. The outcome should differ from Titan while sharing underlying mechanisms. Organic compounds emerge as leading candidates for haze composition. Carbon-based molecules form readily under ultraviolet irradiation. They can grow to substantial sizes. Their optical properties often produce strong scattering. Many organic hazes are highly reflective. This matches Enopotia's observed albedo. Sulfur compounds offer another possibility. Volcanic outgassing or photochemistry might produce sulfur dioxide. Further reactions could create sulfur aerosols. These particles can form reflective hazes under the right conditions. Venus possesses sulfuric acid clouds. Enopotia might host similar chemistry but modified by its unique composition and temperature. The reflectivity itself demands explanation. Enopotia's bond albedo reaches 0.51, meaning the planet reflects 51% of incoming stellar radiation. This exceeds Venus at 0.76 only because Venus represents the solar system's most reflective planet. For a world without Venus's thick sulfuric acid clouds, 0.51 seems extraordinarily high. What makes hazes so reflective? Particle size matters. If haze particles measure roughly the same as radiation wavelengths, scattering becomes extremely efficient. The particles act like tiny mirrors. Each one reflects a fraction of incoming light. Billions upon billions of particles create a cumulative effect. The atmosphere becomes a diffuse mirror. Particle composition also influences reflectivity. Some materials naturally reflect more than others. Organic tholins can be quite reflective depending on their exact chemistry. Sulfur aerosols likewise. Ice crystals, if they exist in upper atmospheric layers, scatter light very efficiently. The haze layer's altitude affects how much radiation it intercepts. Higher hazes encounter more direct stellar radiation. They reflect photons before those photons penetrate deep into the atmosphere. This prevents lower layers from warming. The temperature remains cooler than it would if radiation reached deeper before scattering. Maria Steinruck's observation remains key. The haze composition must differ from known celestial bodies. Nothing in the solar system matches Enoposha's combination of properties. High metallicity atmosphere. Extreme proximity to host star. Thick reflective hazes. Moderate temperature despite intense irradiation. The planet occupies unique parameter space. This uniqueness makes Enoposha simultaneously frustrating and valuable. Frustrating because familiar analogies fail. No solar system comparison works perfectly. Valuable because it expands our understanding of what planets can be. The universe contains possibilities our local neighborhood never sampled. The mystery of haze composition drives ongoing research. Multiple laboratories synthesize candidate materials. They measure optical properties, reflectivity, absorption spectra, scattering efficiency. Then they compare laboratory results against telescope observations. Gradually the list of possibilities narrows. Some candidates get eliminated quickly. Pure water ice hazes wouldn't remain stable at Enoposha's temperatures. Simple methane hazes don't match spectroscopic signatures. Certain sulfur compounds produce wrong optical properties. Each failed match refines the search. Other candidates remain viable but unconfirmed. Complex organic molecules with specific carbon-to-hydrogen ratios. Sulfur compounds mixed with other aerosols. Exotic materials that only form under unusual conditions. Multi-component hazes where different particle types coexist. The true answer might involve combinations nobody has yet tested. Future observations will help. Higher resolution spectra can detect weaker absorption features. These features fingerprint specific molecules. If scientists can identify even trace atmospheric constituents, they can strain haze chemistry. What molecules exist in the atmosphere? What molecules are absent? Both answers matter. Temperature mapping provides another diagnostic. Different haze compositions affect heat distribution differently. Some hazes preferentially absorb certain wavelengths. Others scatter uniformly. By measuring how temperature varies with altitude and location, researchers infer haze properties. The phase curve observations already demonstrated this approach's power. Watching Enopotia orbit Orcaria revealed how brightness changes with viewing angle. Different atmospheric models predict different phase curve shapes. By matching observations to models, scientists determine which scenarios work. That analysis revealed both clouds and hazes likely coexist. Single-layer models failed to reproduce all observed features. Multi-layer models performed better. Condensate clouds at one altitude. Photochemical hazes at another. Each layer contributes different effects. Together they create the complex atmosphere James Webb detected. Cloud composition remains uncertain. At Enopotia's temperatures, various substances might condense. Salt crystals, metal oxides, silicate particles. Each produces distinct signatures. Current observations don't yet discriminate among possibilities. The clouds hide beneath the hazes. Their properties remain inferred rather than directly measured. Particle sizes matter tremendously. Large particles settle quickly. Small particles remain suspended longer. The size distribution affects opacity. It determines scattering efficiency. It influences cloud layer thickness. Without knowing particle sizes, atmospheric models contain free parameters. These parameters get adjusted until model output matches observations. Multiple combinations often work equally well. This ambiguity frustrates precise characterization. Scientists want definitive answers. What molecules? What abundances? What structures? Instead, they get ranges, possibilities, scenarios consistent with data but not uniquely determined. Progress happens incrementally. Each new observation narrows the possibilities slightly. Definitive answers emerge slowly through accumulated evidence. The three-dimensional nature of Enopotia's atmosphere adds complexity. Temperature varies with location. Chemistry shifts between dayside and nightside. Wind patterns transport materials horizontally and vertically. No single measurement captures everything. Comprehensive understanding requires observations from multiple angles, multiple wavelengths, multiple times. Phase curve observations begin addressing this need. By watching the planet throughout its orbit, scientists sample different regions. The dayside during different local times. The nightside under varying conditions. The terminator zone where transitions occur. Each viewing geometry provides unique information. Combined observations build comprehensive pictures gradually. The terminator region proves particularly interesting. This boundary zone experiences permanent twilight. Neither fully day nor fully night. Temperature gradients exist. Chemistry transitions. Molecules stable on the night side might decompose on the day side. The terminator captures both regimes simultaneously. Studying this region reveals how atmospheric processes vary across Enopotia's face. Wind patterns become apparent through phase curve analysis. Temperature differences drive atmospheric motion. Hot gases expand and rise. Cool gases contract and sink. Pressure gradients push air from high-pressure zones toward low-pressure zones. On Earth, these processes create weather systems. Hurricanes, jet streams, trade winds. Enopotia experiences analogous dynamics but under extreme conditions. The permanent day-night divide creates persistent circulation patterns. Hot dayside air tries flowing toward the cooler nightside. But Enopotia rotates as it orbits. The Coriolis effect deflects moving air. Not exactly like Earth's Coriolis force. Tidally locked rotation creates different geometry. Still, the principle applies. Rotating reference frames introduce deflection. Straight-line motion becomes curved when viewed from the rotating surface. Computer models simulate these circulation patterns. They solve fluid dynamics equations across three-dimensional grids. Each grid cell tracks temperature, pressure, density, composition, velocity. The equations govern how these quantities evolve. Energy conservation, momentum conservation, mass conservation, chemical reactions, radiative transfer, all interconnected. Running these simulations requires substantial computing resources. Supercomputers churn through calculations for days or weeks. The output reveals atmospheric structure in exquisite detail. Temperature distributions at various altitudes. Wind speeds and directions. Cloud formation zones. Chemical abundance variations. Researchers compare simulated observations against real telescope data. Does the model reproduce observed brightness temperatures? Does it match phase curve shapes? Do spectral features align? When mismatches occur, scientists adjust model parameters. Different haze compositions. Alternative cloud properties. Modified wind speeds. Each iteration brings models closer to reality. This iterative refinement continues until simulations faithfully reproduce observations. Then scientists trust model predictions about unmeasured quantities. What happens at altitudes telescopes can't probe? How do winds vary with depth? Where do chemical reactions occur? Models extrapolate beyond direct measurements. They fill gaps in observational coverage. Circulation models suggest Enopotia possesses strong eastward equatorial winds. These jet streams transport heat and chemicals around the planet. They moderate temperature extremes. Without such circulation, the day-night temperature difference would exceed what observations show. The fact that nightside temperatures remain relatively warm indicates atmospheric transport operates efficiently, at least in redistributing some heat. Though not perfectly. Significant temperature contrasts persist. More efficient heat redistribution would equalize temperatures further. Jupiter's atmosphere achieves near-uniform temperatures despite receiving more sunlight on some regions. Strong winds distribute heat effectively. Enopotia's weaker redistribution suggests barriers to circulation exist. Perhaps the haze layer inhibits vertical mixing. Separate atmospheric layers might not communicate well. Stable stratification prevents convection. Without convection, heat transport slows. Only horizontal winds redistribute energy. These winds might flow in narrow altitude ranges. Layered structures with different wind patterns at different heights. The atmosphere becomes compartmentalized. Each layer evolving semi-independently. Understanding these dynamics matters for broader exoplanet science. Enopotia represents the most common planetary type in the galaxy. Mini-Neptunes outnumber all other exoplanet categories. Yet our solar system contains no examples. Nothing between Earth and Neptune. This gap prevents direct study. We can't send spacecraft to examine mini-Neptunes up close. Telescopic observations of distant examples provide our only data, making Anapotia incredibly valuable. Every detail learned about this one world informs understanding of billions of similar planets throughout the Milky Way. The knowledge gained here applies broadly. Do all mini-Neptunes possess thick hazes? Do metallicity levels vary systematically? How do formation locations affect atmospheric composition? Anapotia begins answering these questions. It establishes benchmarks, sets expectations, guides future observations of other systems. As more mini-Neptunes get characterized, patterns will emerge. Perhaps certain properties correlate. High metallicity might associate with specific orbital distances. Haze properties might depend on stellar type. Building this statistical understanding requires studying many examples. Anapotia provides the template. The first thoroughly characterized member of this planetary class. Its atmosphere reveals what detailed observations can achieve. Future telescopes will apply similar techniques to additional targets. Each new world refines understanding. Gradually, the population of mini-Neptunes comes into focus. No longer mysterious. No longer poorly understood. Just another planetary type with known characteristics. The broader implications extend to planetary formation theory. How do mini-Neptunes form? Why are they so common? Our solar system's architecture seems atypical. Most planetary systems contain mini-Neptunes. Many orbit close to their stars. Did they form nearby? Or migrate inward from distant birthplaces? Evidence suggests migration. Planets probably coalesced beyond a snow line where volatile ice is condensed. Water, methane, ammonia. These ices provided abundant building material. Protoplanets accreted ice-rich compositions. Then gravitational interactions with the protoplanetary disk caused orbital decay. Planets spiraled inward. Some stopped at current locations. Others continued migrating until stellar proximity halted movement. This inward journey transformed planetary properties. Volatile ices sublimated as temperatures increased. Atmospheres thickened. Surface conditions changed dramatically. What began as cold ice-rich worlds became hot mini-Neptunes with steam atmospheres. Anapotia likely experienced this evolution. Its high atmospheric metallicity supports the migration hypothesis. If the planet formed in place near Orcaria, it couldn't have accumulated so much ice. The formation region was too hot. Heavy elements wouldn't concentrate efficiently. But forming beyond the snow line explains everything. Ice-rich accretion. Subsequent inward migration. Heating and atmospheric evolution. The current state reflects this history. Confirming this scenario requires additional evidence. Studying Anapotia's interior structure would help. Does a massive ice layer exist beneath the atmosphere? Or has prolonged heating evaporated most volatiles? Current observations constrain bulk composition but not detailed internal structure. Mass and radius measurements limit possibilities. Density indicates substantial volatile content. But whether that volatile material resides in a deep ocean, a thick atmosphere, or distributed throughout the interior remains uncertain. Different internal configurations produce similar observable properties. Degeneracy limits what we can infer from external measurements alone. Future observations might break this degeneracy. Detecting atmospheric escape could reveal interior processes. If Enopotia actively loses atmosphere to space, that implies internal volatile reservoirs continue supplying replacement material. Measuring escape rates constrains interior volatile abundance. Similarly, detecting trace atmospheric constituents reveals outgassing. Volcanic activity releasing gases from the interior produces specific chemical signatures. Sulfur compounds. Noble gases. Isotopic ratios. Each provides clues about internal composition and processes. No evidence for ongoing outgassing exists yet. Observations haven't reached necessary sensitivity. But next-generation telescopes might detect these subtle signals. The extremely large telescope under construction will dwarf current instruments. Its mirror spans 39 meters. Collecting area exceeds existing telescopes by factors of 10 or more. With such light-gathering power, faint signals become detectable. Spectroscopic resolution improves. Noise levels drop. Precision increases. ANDES, the telescope's high-resolution spectrograph, specifically targets exoplanet atmospheres. Simulations predict it will detect carbon dioxide in Enopotia's atmosphere with high confidence. Water vapor signatures will strengthen. Methane might become detectable if present at sufficient abundances. Each molecule identified adds another piece to the compositional puzzle. Beyond individual molecules, isotopic ratios provide powerful diagnostics. Different isotopes of the same element behave chemically identically but have different masses. Measuring their relative abundances reveals formation conditions and evolutionary history. For example, the deuterium to hydrogen ratio indicates where water originated. Deuterium enrichment suggests cometary delivery. Solar values indicate primordial nebular water. Intermediate ratios imply mixing. Similarly, carbon and oxygen isotope ratios constrain chemical processes. Equilibrium chemistry produces specific ratios. Disequilibrium processes shift ratios differently. By measuring multiple isotopic systems, scientists reconstruct planetary history. Did Enopotia accrete material locally or from distant regions? Has atmospheric chemistry reached equilibrium, or does active disequilibrium persist? These questions get answered through isotopic analysis. Current technology can't yet measure exoplanet isotope ratios reliably. Signals are too weak. Spectral features too subtle. But upcoming instruments push toward this capability. Within a decade, isotopic measurements might become routine for favorable targets. Enopotia qualifies as favorable. Bright host star. Large planetary signal. Frequent transits. Everything that made it accessible to James Webb also benefits future observations. The planet will remain a priority target as new capabilities come online. Each technological advance enables deeper investigation. The transition from Hubble's frustrating non-detections to Webb's breakthrough demonstrates how instrumentation drives progress. Hubble tried characterizing Enopotia's atmosphere multiple times. Every attempt yielded featureless spectra. The thick haze defeated Hubble's capabilities. Scientists knew something interesting existed but couldn't penetrate the veil. Then Webb arrived with infrared sensitivity and superior resolution. Suddenly the atmosphere revealed its secrets. Not completely. Mysteries remain. But the transformation was dramatic. From essentially zero information to detailed characterization. Future telescopes will enable similar leaps. What seems impossible today becomes routine tomorrow. The techniques developed for Enoposha transfer to other worlds. Phase curve analysis, multi-wavelength spectroscopy, three-dimensional modeling. These methods apply broadly across exoplanet science. As observational capabilities expand, so does the sample of characterized atmospheres. Soon dozens of mini-Neptunes will have detailed measurements. Then hundreds. Patterns will emerge. Outliers will become apparent. Enoposha's place in the broader population will clarify. Is it typical or unusual? Do most mini-Neptunes share similar properties, or does diversity dominate? Right now we can't answer these questions. The sample size remains too small. But the foundation exists. Methods work. Technology advances. The coming decade promises revolutionary progress in understanding these common yet mysterious worlds. Understanding these worlds matters because they dominate our galaxy. Every survey reveals them in abundance. Around nearly half of Sun-like stars, mini-Neptunes orbit. Yet we possess no local example. No planet in our solar system occupies this size range between Earth and Neptune. This creates a knowledge gap, a blind spot in our understanding of planetary possibilities. Studying Enoposha fills that void. What scientists learn here applies elsewhere. Broadly, the planet serves as a Rosetta Stone for decoding an entire population. This connection between individual case studies and broader populations drives modern astronomy. Single objects like Enoposha become laboratories, test beds for theories. Their properties constrain models. Their behavior reveals physical laws. Then those lessons transfer to hundreds of similar worlds, eventually thousands. The process resembles medical research. Studying individual patients reveals disease mechanisms. Those mechanisms then inform treatment for entire populations. Similarly, characterizing one mini-Neptune illuminates the nature of countless others. Consider formation scenarios. How do mini-Neptunes form? Where in protoplanetary disks do they originate? Do they migrate inward or form in place? Enoposha's composition provides clues. Its extreme atmospheric metallicity suggests formation beyond the water ice line, where volatiles condense. Then inward migration brought it close to its star. Heat evaporated outer layers, leaving behind today's configuration. But questions remain. How much mass did it lose? What did the original planet look like? Computer simulations attempt reconstruction, starting with observed properties, working backward through time. Each simulation makes assumptions about disk conditions, migration rates, atmospheric escape processes. Then predictions emerge. Testable predictions. Future observations either confirm or refute them. The distinction between water worlds and supervenuses becomes crucial here. Early assumptions favored water-rich compositions. The name Enoposha itself means large body of water, chosen when scientists believed they'd found an ocean planet. But recent evidence challenges this picture. Carbon dioxide signatures, reflective hazes, temperature profiles, all point toward Venus-like conditions. Dense carbon dioxide atmosphere, Thick photochemical haze layers. Minimal water at the surface. This revision matters. It changes formation theories. Affects habitability assessments for similar planets. Shifts the search strategy for potentially life-bearing worlds. Why did the water world interpretation fail? Multiple reasons converge. Internal structure models struggled to match observations. Pure water envelopes required unrealistic rock-to-ice ratios. Spectroscopic signatures didn't fit expectations. Water absorption features appeared weaker than predicted. Carbon dioxide signatures stronger. The cumulative evidence tilted toward the supervenous scenario. But certainty remains elusive. The planet still guards its deepest secrets. Beneath those reflective clouds, what truly exists? Solid surface, supercritical ocean, gradual transition from gas to liquid to solid. Nobody knows yet. This uncertainty frustrates scientists. After decades of observation, hundreds of hours of telescope time, advanced space missions, yet fundamental questions persist. The frustration drives innovation. New techniques develop. Novel approaches emerge. Researchers push instrumentation to its limits. Then beyond. Because answering these questions matters. Not just for Enopotia. For exoplanet science generally. The methods that crack this mystery will unlock others. The instruments that penetrate this haze will pierce different veils. Progress compounds. Each breakthrough enables the next. Future missions target these challenges specifically. Ariel, the atmospheric remote sensing infrared exoplanet large survey, will survey hundreds of exoplanet atmospheres. Launch scheduled for 2029. Its primary goal involves characterizing atmospheric composition across diverse planets. Mini-Neptunes feature prominently. The mission will observe Enopotia multiple times. Different wavelengths. Various orbital phases. Building comprehensive datasets. Comparing it systematically with other mini-Neptunes. Population studies reveal patterns invisible in individual cases. Trends emerge. Correlations appear. Between planetary mass and atmospheric composition. Between stellar properties and planetary characteristics. Between formation location and final architecture. Ground-based telescopes continue advancing too. The extremely large telescope represents the next giant leap. Its 39-meter mirror dwarfs existing facilities. Light collecting area exceeds current telescopes by more than tenfold. This raw power translates into sensitivity. Faint signals become detectable. Spectroscopic resolution improves dramatically. Noise drops. Precision climbs. The Andes spectrograph specifically targets exoplanet atmospheres. Simulations demonstrate its capabilities. Carbon dioxide detection reaches high confidence. Water vapor signatures strengthen considerably. Methane becomes detectable if present. Each molecule adds context. Constrains models. Narrows possibilities. Beyond molecular detection, isotopic measurements loom on the horizon. Different isotopes of the same element behave chemically identically. But mass differences create subtle spectral shifts. Measuring these shifts reveals formation history. Deuterium to hydrogen ratios indicate water origins. High ratios suggest cometary delivery. Solar ratios imply primordial nebular water. Carbon and oxygen isotopes constrain chemical evolution. Equilibrium versus disequilibrium processes. Current technology can't reliably measure exoplanet isotope ratios. Signals remain too weak. But approaching instruments push toward this threshold. Within a decade, isotopic measurements might become routine. Enopotia stands ready. Its bright host star. Large planetary signal. Frequent transits. Everything favoring detailed study. The planet will remain a priority target. As new capabilities come online, each technological advance deepens investigation. Think about the progression. Hubble tried characterizing this atmosphere. Multiple attempts. Every observation yielded featureless spectra. Thick haze defeated Hubble's capabilities. Scientists knew something interesting existed, but couldn't penetrate the veil. Then Webb arrived. Different wavelengths. Superior resolution. Infrared sensitivity. Suddenly the atmosphere revealed its nature. Not completely. Mysteries persist. But transformation was dramatic. From essentially zero information to detailed characterization, future telescopes will enable similar leaps. What seems impossible today becomes routine tomorrow. This progression mirrors the broader arc of exoplanet science. 30 years ago, no confirmed exoplanets existed. Zero. Scientists could only speculate. Now thousands populate catalogs. Hundreds have characterized atmospheres. The field transformed completely. From theoretical possibility to observational reality. Enopotia represents one milestone in this journey. A significant one. The first sub-Neptune with directly detected thermal emission. The first mini-Neptune with detailed atmospheric characterization. These firsts matter. They establish baselines. Prove feasibility. Inspire further investigation. But individual milestones fade into the bigger picture. What really matters is cumulative understanding. As more mini-Neptunes get characterized, patterns emerge. Some will resemble Enopotia. High metallicity. Thick hazes. Reflective atmospheres. Others will differ. Perhaps clearer atmospheres. Different compositions. Varied temperature structures. This diversity reveals formation pathways. Environmental influences. Evolutionary trajectories. The goal isn't understanding one planet. It's understanding planetary systems. How they form. How they evolve. What possibilities exist. Enopotia teaches humility too. Scientists predicted a water world. Named it accordingly. Built models. Made confident statements. Then observations overturned expectations. The planet wasn't what anyone thought. This happens repeatedly in science. Predictions fail. Assumptions collapse. Reality surprises. The lesson isn't that scientists were wrong. It's that nature exceeds imagination. Planets don't read textbooks. They follow physics. And physics permits configurations nobody anticipated. Embracing surprise drives discovery. When observations contradict theory, theory must adapt. The supervenous interpretation brings its own implications. If Enopotia resembles Venus more than a water world, what does that mean? Venus in our solar system underwent runaway greenhouse warming. Thick carbon dioxide atmosphere trapped heat. Surface temperatures climbed to 460 degrees Celsius. Hot enough to melt lead. Hostile to any known life. Does Enopotia follow a similar path? Its temperature exceeds Venus. Its atmosphere appears even thicker. The comparison suggests extreme conditions. Crushing pressures. Searing heat. Corrosive chemistry. Nothing hospitable. Yet studying these extremes matters. Understanding planetary climate requires examining edge cases. How greenhouse effects operate at maximum intensity. How atmospheres respond to extreme stellar irradiation. Where the boundaries of habitability lie. Habitability itself becomes a complex question. Enopotia certainly can't host life as we know it. Too hot. Too harsh. But could life exist elsewhere in the system? On moons? In outer regions? And what about similar planets around different stars? Cooler hosts might permit mini-Neptunes at habitable distances, with temperatures allowing liquid water. Whether such planets could actually support life remains unknown. Their thick atmospheres might prevent surface habitability. But subsurface oceans become possible, protected by overlying layers, fed by internal heat, similar to Europa or Enceladus. Scaled up, the possibilities multiply. Each discovery raises new questions, opens new avenues. This cascade of inquiry defines scientific progress. Answers generate questions. Solutions reveal deeper mysteries. The process never truly ends. Each generation of astronomers pushes further, uses better tools, achieves finer measurements. But the horizon keeps receding. There's always more to learn. Enopotia demonstrates this perfectly. After 15 years of study, major uncertainties remain. Yet progress is undeniable. From mysterious featureless spectra to detailed atmospheric maps. From wild speculation to constrained models. The journey continues. Future observations will refine understanding, resolve remaining debates, but they'll also unveil new mysteries, unexpected phenomena, puzzling contradictions. That's the nature of exploration. The frontier constantly shifts. What seemed cutting-edge yesterday becomes routine today. What seems impossible today becomes achievable tomorrow. And through it all, Enopotia orbits its star, reflecting light, radiating heat, waiting for the next telescope, the next technique, the next breakthrough. A world 48 light-years away, yet intimately connected to our understanding of planets everywhere. That's the power of modern astronomy. Reaching across cosmic distances, decoding alien worlds, piece by piece, spectrum by spectrum, building a comprehensive picture of planetary diversity. And Enoposha's story is far from finished. Looking back at Enoposha's journey from discovery to revelation, one thing becomes clear. This planet dismantled every assumption we brought to it. Scientists expected a water world. Got a super Venus instead. Anticipated straightforward observations. Encountered impenetrable hazes. Thought they understood mini Neptunes. Realized they'd barely scratched the surface. The transformation of our understanding mirrors the scientific process itself. Start with observations. Build models. Make predictions. Then let reality have the final word. When Enoposha refused to match expectations, scientists didn't force the data to fit theories. They rebuilt the theories. That flexibility defines good science. The willingness to abandon cherished ideas when evidence demands it. But this story extends beyond one planet. Enoposha represents billions of similar worlds scattered throughout the galaxy. Mini Neptunes dominate planetary populations. Yet our solar system contains none. This gap creates opportunity. Every detail learned about Enoposha informs understanding of countless others. The metallicity measurements. The haze properties. The temperature distributions. All transfer to broader populations, making this single world extraordinarily valuable. Consider what remains unknown despite intensive study. The exact haze composition. The internal structure beneath the atmosphere. Whether volcanic activity persists. The formation history details. Each question drives future research. Motivates new observations. Pushes technological development. Scientists won't stop until answers emerge. And each answer will generate fresh questions. Deeper mysteries. The cycle continues indefinitely. The upcoming decade promises dramatic advances. Aerial launches in 2029, surveying hundreds of exoplanet atmospheres. The extremely large telescope nears completion, offering unprecedented light-gathering power. Andes will achieve spectroscopic resolution beyond current capabilities. These instruments will dissect Enoposha's atmosphere with precision today's technology can't match. Carbon dioxide abundances. Water vapor distributions. Methane detection if present. Isotopic ratios revealing formation conditions. The planet will yield more secrets. Reluctantly perhaps, but inevitably. Yet technology alone doesn't drive discovery. Creativity matters equally. The phase curve technique that unlocked Enoposha's secrets required innovative thinking. Not just building better telescopes, but using existing instruments differently. Watching the planet through complete orbits instead of just transits. That conceptual leap made breakthroughs possible. Future progress will demand similar creativity. Novel approaches to stubborn problems. Unconventional techniques applied to familiar targets. The broader implications ripple outward. Understanding mini Neptunes affects planetary formation theory. Influences habitability assessments. Guides the search for life beyond Earth. If the most common planetary type remains poorly characterized, our cosmic census stays incomplete. Enoposha helps fill that gap. One world at a time. One observation at a time. Building comprehensive knowledge through accumulated evidence. The name Enopotia carries irony now. Chosen to honor a presumed water world, now associated with a super-Venus instead. Yet the name endures, connecting this distant planet to Earth's linguistic diversity, honoring the Maasai people's language, their relationship with natural elements. The name reminds us that science exists within human culture, not separate from it. Discoveries carry meaning beyond technical details. They connect us to the cosmos, to each other, to our place in the universe. 48 light-years separates us from Enopotia, an unbridgeable physical distance. Yet telescopes collapse that gap. Photons that left the planet decades ago arrive at our detectors, carrying information, encoding atmospheric properties, temperature distributions, chemical compositions. We decode those messages, reconstruct distant realities, build understanding across cosmic voids. That's humanity's unique capability. Not physical exploration of every world, but intellectual exploration through observation and analysis. The frustration scientists experienced chasing Enopotia for over a decade has transformed into satisfaction. The white whale finally yielded. Not all its secrets, but enough. Enough to revolutionize understanding. Enough to guide future research. Enough to demonstrate that persistence pays off. Some problems require patience, better technology, novel approaches, but solutions eventually emerge. For those willing to keep searching. What started as a simple discovery announcement in December 2009 has evolved into a comprehensive case study, spanning multiple telescopes, dozens of research teams, hundreds of publications, thousands of hours of observation and analysis, all focused on understanding one world. That investment reflects Enopotia's importance. As a representative of the galaxy's most common planetary type, as a laboratory for atmospheric physics, as a window into planetary formation and evolution, the investment will continue. For years, decades, until many Neptunes transition from mysterious to understood. The journey from featureless spectra to detailed characterization demonstrates scientific progress in miniature. Initial observations revealed nothing. Telescopes improved. Techniques advanced. Suddenly information flooded in. This pattern repeats throughout astronomy. What seems impossible becomes routine. What appears unknowable becomes measured. The horizon constantly recedes. New questions replace answered ones. The frontier shifts but never disappears. Enopotia orbits its red dwarf star. Perpetual day facing perpetual night. Thick hazes reflecting starlight. Carbon dioxide aerosols suspended high. Water vapor mixed throughout. Temperature gradients driving winds. Chemistry creating exotic compounds. All of this happening right now. 48 light-years away. Independent of human observation. The planet doesn't care whether we understand it. It simply exists, following physical laws, evolving on geological timescales, waiting for our technology to catch up with our curiosity. And that's the fundamental truth about exoplanet science. The planets are already there. Already exhibiting their properties. Already holding their secrets. Our challenge isn't making them reveal anything. It's developing the capability to see what's already present. Building better instruments. Applying smarter techniques. Asking sharper questions. The universe provides answers. We just need to learn how to listen properly. Anaposha listened to no one. It kept its secrets for over a decade. Then James Webb arrived with the right tools. The right approach. The right questions. And the planet responded. Not through cooperation, but through physics. Photons carrying information. Spectra encoding composition. Thermal emission revealing structure. All there for anyone with eyes sensitive enough to see. The breakthrough wasn't persuading the planet to talk. It was finally learning its language. That's where this story stands now. Partially told. Substantially advanced. But far from complete. The next chapters will be written by upcoming telescopes. Future researchers. New techniques nobody has invented yet. Each generation pushes further. Sees deeper. Understands better. Building on previous work. Standing on the shoulders of those who came before. The process has no end point. No final revelation. Just continuous refinement. Endless discovery. Perpetual wonder at what exists beyond our world. Beyond our solar system. Beyond our current understanding. 48 light-years away. A planet named for water. Probably resembling Venus. Definitely defying expectations. Teaching lessons about planetary diversity. About scientific humility. About the value of persistence. About the rewards of looking up and asking what's really there. That's Anaposha. The mysterious world wrapped in thick clouds. Finally beginning to emerge from shadow into light.